Finish up the alkynes chapter. It takes alkynes to make a world. All right, Organic Chemistry 1. We left off somewhere around here. The very last section of Chapter 9, we had covered all of these reactions that you see on here. But let's face it, what we really want to look at are the summary of reactions where we can actually see some structure. So we have all these structures here. And let's just kind of take a quick overview here of everything that we looked at. Let's start with reaction number 1. So over here, that was the elimination of Geminal Dihalide, so double elimination followed by deprotonation. And then we added water as a proton source to make a terminal alkyne. We said you can do the exact same thing with a vicinal dihalide, so the exact same thing. Then we go up to number 2, that was hydrohalogenation. So excess hydrohalogenation of an alkyne gives you this. And I said the mechanism isn't, that well understood, so we discussed that a little bit. Next was the addition of one equivalent of HX, whether it's HCl or HBr. We get Markovnikov addition. And then we get into some neat hydration reactions. When you add water in a Markovnikov fashion, you have to use acid and water, sulfuric acid and water, but you've also got to use mercuric sulfate. So that's HgSO4, and that is to allow the alkyne to react. It's not reactive enough on its own. You just throw acid at it. It won't do anything. So first you produce an enol, and then that enol undergoes the tautomerization process to give you a methyl ketone. So that's a methyl ketone there. Next, we looked at anti-Markovnikov addition of water across the triple bond, and we said that that's done with borane and THF. No, we don't use that. We use a hindered borane, R2BH, okay? And we said there's several hindered boranes you can use. We said 9-BBN would work. We said dicyamal borane, that'll work. And then I said that sometimes we just write R2BH like that. I showed you a variation that the ACS uses, but that's anti-Markovnikov addition. And when that occurs, you end up with an enol that tautomerizes to give you an aldehyde. So aldehyde synthesis. Next one was adding one equivalent of a halogen. Gives you the halogen, and they're usually added in the trans fashion. Then I said if you treat it with excess, well, that just halogenates everything. Okay, so you end up with a tetrahalide. Next one is ozonolysis. Remember that the second step of the ozonolysis of an alkene was DMS or zinc and water. But here we use just water, and we end up with a carboxylic acid and carbon dioxide. If you have a terminal alkyne, you end up with 2 carboxylic acids if you had an internal alkyne. Then we learned one of the most important reactions of all, the alkylation reaction. So alkylation, which is where you do, sorry, I circled the wrong one. This one here, where you deprotonate using sodium amide. Then you treat it with some kind of methyl or primary alkyl halide to make a carbon-carbon bond. Huge deal, right? Anytime you make a carbon-carbon bond, it's a big deal. In organic chemistry, hydrogenation, complete hydrogenation makes an alkane. Then we looked at hydrogenation with a poison catalyst like Lindlar's catalyst, or the P2 catalyst gives you a Cis Alkene. And then the last thing is sodium metal reduction, which gives you a trans alkene. Why? Because it proceeds through a radical anion intermediate. Well, there's a lot of information there, isn't there? There is a lot of information, but instead of just sitting down and trying to go, okay, hydroboration oxidation goes from here to here, this goes from here to here. I think a better way to learn all these reactions is to just jump in the deep end of the pool and start trying something, okay? Try to do some synthesis problems and see if you can, use those. And if you have to go back and look at your notes, then so be it. It's no big deal. So what we're going to do is we're going to start with these 3 questions. I'm going to go over to a blank document here just so I have a little more room. This one, yeah, right here. So alkynes practice. And we're going to start with that first question that I had labeled as 9.29a. And you can see that we're changing the carbon skeleton. Here we've got 4 carbons, and here we've got 6 carbons. We're adding 2 carbons overall. Here's my first question to you of the day. How many ways do we know how to make carbon-carbon bonds so far in this class? Could anybody tell me how you would make, because you're going to have to make a carbon-carbon bond. And we're making a cis alkene. How many ways do we know how to make carbon-carbon bonds? Anybody? I can tell you that we literally have one way. Okay, you've only learned one way to make carbon-carbon bonds in this class, and that is to take a terminal alkyne. So we would want to start with some kind of terminal alkyne like this, and then you can rip this proton off and treat it with iodoethane. Okay, so that means that we're going to have to take this, treat it with sodium amide in the first step, and in the second step, we treat it with ethyl iodide. Now the question becomes, how do we go from one butene to one butene? Well, we only know one way to make an alkyne, and that is from a dihalide. We don't know how to make, I guess we do know how to make a geminal dihalide, but a better approach would be to make a vicinal dihalide. So that would come from this dihalide. So you could put two bromines on here like this, okay? All right, and we see that that can come from our starting material. All we have to do is brominate it. So there you go, we've solved the entire problem. So what's our first step going to be? First thing we're going to do is we're going to add bromine. And you can pick a solvent if you want. You could put chloroform, CHCl3. You can put dichloromethane, which our book likes as a solvent for bromination. And that's going to add one bromine to each one of these carbons. Okay, that's a chapter 8 reaction. So we end up with this. So we have a bromine here and a bromine here. Well, how did we say that we would convert this to 1-butene? We have to do the double elimination. First step is excess sodium amide. Who could tell me what the second step would be here? So I do the double elimination with the two equivalents of sodium amide. Then I do a deprotonation. What's my next reagent have to be? Exactly. Yes. It's got to be water, doesn't it? Right, because you need water as a source of protons to put in this proton at the end. That comes from H2O. All right, there we go. So now we have 1-butene. Now we can add the ethyl group, or add 2 more carbons to the molecule. So in the first step, we're going to treat it with sodium amide. That will rip off this proton. Then you get the alkyne, and then you do an SN2 with ethyl iodide, like this. And now you've got this compound. So you've got 3-hexyne. So this would be 3-hexyne. And then if we want to reduce it, to cis, so this molecule here, this would be called cis 3-hexene. Could anybody tell me what the conditions are to reduce and make the cis molecule? We want to make cis. What would the conditions be here for a cis reduction of an alkyne to a cis alkene? Yep, Luke's you're part of the way there for sure. You definitely need hydrogen gas, yep. But you also need Lindlar's catalyst. Yes, 100% correct. Great. So you need hydrogen and you need Lindlar's catalyst. There you go, my friends. That's the whole problem solved, just like that. Let's count the steps. We've got 1, 2, 3, 4, 5, 6. So a 6-step synthesis, that's something, you know, that's quite a few steps. Let's take a look at the next one. So this is 9.29b. So let me erase this just so we can see a little bit better. This is 9.29b. So we're taking 1-butene and we want to make an aldehyde. How many ways do we know how to make an aldehyde? Unless we're talking about ozonolysis of an alkene, we only know one other way. But we don't want to do ozonolysis of an alkene to make an aldehyde, because if you were to treat this with ozone followed by DMS, that would give you this aldehyde, 1, 2, 3 carbons done, right? You'd have only 1, 2, 3 carbons, and here you have 1, 2, 3, 4. So that is not going to work, right? It's impossible. You cannot use that as a way to do this chemistry. So you've got to come up with something else. What if, instead of that, what if we started out with 1-butyne? If we had 1-butyne, then we could do the anti-Markovnikov addition of water using 9-BBN followed by hydrogen peroxide and sodium hydroxide to give us the enol that tautomerizes to give us the aldehyde. So now the question becomes, okay, well, how do I go from 1-butene, how do I go from 1-butene to 1-butyne? Well, we just solved that in the last problem. So there's no need to really go over that in detail. Let's just write down the steps. I'll be a little bit quicker this time. So first thing we're going to do is we're going to treat it with bromine. Then we treat it with excess sodium amide. So the amide. Then we're going to treat it with water. Now we've got our 1-butyne molecule. Okay. And now what you're going to do is you're going to treat this with 9-BBN. And in the second step, you're going to use hydrogen peroxide and sodium hydroxide, and it's a anti-Markovnikov addition of water. So look, you've got this blue carbon, you've got this red carbon. The red carbon has more hydrogens on it. It has 1 hydrogen. The blue carbon has no hydrogens. Therefore, since it's anti-Markovnikov, it's the red carbon that's going to take the hydroxyl and the blue carbon that's going to take the hydrogen. So we end up with something that looks like this. We end up with 1, 2, 3, 4, and the hydroxyl is over here. Okay, and then the proton would be here, the one that you added from the during the reaction. So this is an enol, right? You've got a carbon that's got an alkene and an alcohol on the same carbon. This is an enol, and enols are not stable, generally speaking. It is going to undergo tautomerization to give you that aldehyde. And there we go. That one's done. Another one complete. Give me a thumbs up if you follow me on the rationale for that one. Whole 9-BBN thing and the enol that you form. Okay, cool. All right, well, let's move on. So let's look at 9.29C. So this is 9.29C. And then this one, we want to take 1-butyne. So there's 1-butyne, and we want to make 2-butanol. 2-butanol. So we want to make an alcohol, right? We're going from an alkyne to an alcohol. I mean, really, how many ways do we have to make an alcohol? The only thing that I can think of off the top of my head is if we had 1-butene, right? If we had 1-butene, then all we have to do is just a straightforward Markovnikov addition of water across that double bond. The rich get richer, and we're done, just like that. So the question becomes, well, how do we get from 1-butyne to 1-butene? Could anybody tell me the conditions you would need? Because we learned 2 sets of conditions to reduce an alkyne to an alkene. Could anybody tell me which one of those I would use in this case? Okay, so sodium metal reduction. The thing is and this is something I went over quickly with you the other day, sodium metal reduction of a terminal alkyne will not work. Let's get the red highlight. This will not work, does not work. The only way that you can reduce a terminal alkyne to an alkene is to use hydrogen gas and Lindlar's catalyst. Lindlar's catalyst. The sodium metal reduction does not work with a terminal alkyne. And so now we end up with 1-butene, and all we have to do is treat that with aqueous acid. And so that one was just a 2-step problem. You only have step 1, 2, and it's done. But keep in mind that you cannot do sodium metal reduction on a terminal alkyne. It has to be an internal alkyne. And if you're wondering, what does that mean? Well, again, it's when you have an R group on each side. Then you can use sodium and liquid ammonia, and that will give you a trans alkene like that. Okay, you can do it then, but not on a terminal alkyne. All right, well, there's the first three done. Let's turn the page, or I'm going to go to my next slide here in my notes. Let's do the next one. And this is, we're going to have to dig into the recesses of our chapter 8 chemistry. So this is 9.29D. We're taking 1-butyne, and we want to make 1-butanol. So let me just pencil in 1-butanol here, like that. Well, I can tell you right now that the first thing that pops into my mind is that if you have a primary alcohol, which is where you have an alcohol on the end of a molecule like this, the only thing that we have is anti-Markovnikov addition, right? Using borane and THF that we learned in chapter 8. So the only way that we could do this would be by starting with this, and then first treat it with borane and THF, followed by hydrogen peroxide and sodium hydroxide. That's the only thing we have. So now the question becomes, how do we get from here to here? Well, we just did it in the last problem. We said you take this and you reduce it with hydrogen gas in Lindlar's catalyst. That gives you 1-butene, 1, 2, 3, 4. And then you just do the anti-Markovnikov addition of water across that double bond. Chapter 8 chemistry. It never goes away. Hydroboration oxidation. It's very important chemistry. Always shows up in organic chemistry. You can't, that's one of those reactions, you can't really dodge it. You can't say, oh, I'm going to just ignore that one. It comes up all the time. Even when you're halfway through organic chemistry too, I'll still be like, you remember this? You know, talk about it all the time. So let's try the next ones. Let's see here. Let's do E. Oh, let me see where my notes go. E, okay. Let's see here. So E is where we go from 1-butene. So in E, we go from 1-butyne, sorry. This seems to be the reagent of the hour. And we're trying to make this compound. Let's see my notes here. We've got 1, 2, 3, 4, 5, 6 carbons. And then we have a bromine here. And we've got a bromine here. So this one, you've got to be very careful with it. Okay, this one is a question that they love to ask, and you've got to be very careful. So let me tell you why I'm saying that, okay? Because my question to you is, if you do bromination, because at some point we're going to have to do a bromination with Br2, because we've got 2 bromines on 2 adjacent carbons. Does bromination occur via syn addition or anti-addition? That's my question to you. Bromination, is it syn addition or is it anti-addition? Could anybody answer that? This is something that we saw in the alkenes chapter. Yes, absolutely. It's anti-addition. It's anti-addition bromination. So if the bromines are on opposite sides, right? You see this one is coming out of the page. This one is going in. That means the only possible alkene that you could start with would be this trans alkene. That's the only possibility. You could not start with this compound, because if you do anti-bromination to that, you're not going to end up with the right compound. It will not work. You've got to start with the trans alkene, because when you add the bromines to it, one's going to go up and one's going to go down. You end up with the right product. Therefore, the question becomes, okay, well, number one, we don't even have enough carbons. We've only got 1, 2, 3, 4. Here you have 1, 2, 3, 4, 5, 6. We've got to add 2 carbons, and then we've got to reduce to a trans alkene. So I'm kind of running out of space here, aren't I? Let me see. The first thing we're going to do is we're going to add the 2 carbons. We already saw how to do that this morning. You take the molecule, you treat it with sodium amide to rip off the terminal proton. Then you add ethyl iodide because you want to add 2 carbons on the end. Okay, so you can write it like this. That's ethyl iodide. You can write ET, which stands for ethyl. You can write iodide. If you want to use the bromide, you put ethyl bromide. If you want to use the chloride, you can do that. And that will give you this compound. So now you've got this. You can write it like this, like this. Doesn't matter because those are sigma bonds. Now we want to reduce this to the transalkene. How do we do that? We saw that the transalkene is formed from an alkyne by using sodium metal reduction. So we put sodium, and we have liquid ammonia, like that, and that gives us our desired transalkene. And now all we have to do is take it and treat it with bromine. That's it, and we're done. Do you read me on this one? And the reason I say that is because Klein loves these questions where you have a trans or a cis, and you have syn dihydroxylation, anti-dihydroxylation. He gets into it even more in organic chemistry too, but he loves to ask these questions. So let's do one more that's in the exact same vein. Let me show you. So this is F. So let's scribble it down here. Okay, very similar vein. The first part's going to be identical to the last problem. But now we want to make this compound where you have, oh shoot, I drew the wrong thing here. There we go. You've got 1 bromine going back in the page, and you've got 1 bromine coming out of the page or the screen, what have you. So to start with, when we do our bromination in the very last step, okay, this is a retrosynthesis arrow. I'm thinking backwards. What I need to start with the cis alkene or the transalkene to do the bromination on. Remember, this one's down and this one's up. In this molecule, would I start with the cis or the trans? Exactly. I'm going to have to start with the cis because the bromines are already in the right place. So I'm looking at this and I'm saying, well, my alkene's got to be shaped like this. It's got to be in a cis configuration where the 2 ethyl groups are on the same side, so to speak. And thus, what we're going to start with will be the cis alkene. We already know how to add the 2 carbons. We use sodium amide in the first step. Then we use ethyl iodide in the second step. That gives us 3-butyne, this molecule. Then we want to reduce that to the cis alkene, like this. We already looked at that many times. So hydrogen and Lindlar's catalyst. And then we're going to treat that with bromine. And there you go. Hot dog, we have a wiener. Just like that, we solved another problem. Nothing to it. Nothing to it at all. Well, there's not nothing to it, but everybody with me on that? Any questions about those ones, those synthesis problems? The reason why I go over so many synthesis problems at the end of the chapters is because, based on my experience, this is the best way to master your reactions, is to put them into practice over and over and over. With that in mind, let's take a look at a couple of other questions here. So just bear with me while I find them. Yeah, I thought we would just pick a few problems from the textbook. I know that a lot of you, in fact, almost all of you, I'm sure, are doing every single suggested practice problem, and I highly recommend that. But this will just give you a little bit of jump on that if you haven't started it already. Let's try naming a couple of compounds just for fun. What if we wanted to name B? So this is, what if we wanted to name this one here? How would we do that? If I highlight this carbon in yellow and I highlight this carbon in red, could anybody tell me where I would start numbering the chain? Would I start on the red carbon or the yellow carbon? Exactly. What my students are saying is they said, okay, Mr. Dion, you've got to start on the red carbon because the carbon chain is all of this, the longest carbon chain, but you want to give the lowest possible number to the double bond. So you're going to say 1, 2, 3, 4, 5, 6. So this is some kind of 2-hexyne. I have 4,4-dichloro, and then I put that all together. So I've got 4,4-dichloro 2-hexyne. And if you put hex-2-ine, that's fine as well. Could anybody give me the name of C? Just throw it out at me really quickly. And again, it doesn't have to be quick. It's not a race. But can anybody tell me the name of C? Just, hey, I know what this is. It would be 1-hexyne, right? Exactly. So this is 1-hexyne. Yep. So we've got that, right? We would number 1, 2, 3, 4, 5, 6. So this is 1-hexyne. Hexyne. Okay. The next one, I'm not sure if we did this one or not. I can't remember, but if we count here, this one's a good one, actually. You have to be pretty careful on this one. The longest carbon chain is 1, 2, 3, 4, right? Or you could put the 4th carbon up here. Either way, you get the same thing. You have a 3-bromo and a 3-methyl, 1-butyne. So we put that all together. We've got 3-bromo, 3-methyl, 1-butyne. And remember that the bromo comes first because B comes before M in the alphabet, and we put the substituents in alphabetical order. All right, let's take a look at another problem. Again, this is, you can see I copied and pasted this directly from the textbook. Draw the products of each of the following acid-base reactions and then predict the position of the equilibrium in each case. So this is just acetylene here. They've just highlighted the 2 hydrogens explicitly. This is, remember, this is called butyllithium. Butyllithium. And we call that just BULI, like that. So butyllithium. What's going to happen here is your carbanion is going to rip a proton off of here so that you're going to end up with sodium acetylide. So you end up with this, or I guess here it would be lithium acetylide, wouldn't it? And then you also end up with butane. Well, what's the proton donor? It's the alkyne, and that alkyne has a pKa that's equal to 25, and the conjugate acid is butane, which has a pKa equal to 50. Well, what's a higher number? 50 is higher than 25. It's a lot higher when we're talking about logs. We're talking about orders of magnitude of 10, right? Each pKa unit represents an order of 10 or a factor of 10. And so this is a much weaker acid. And so the equilibrium is going to lie to the side of these two, okay, of the lithium acetylide and the butane. So that means that butyllithium is a dandy base for deprotonating a terminal alkyne. What about the next reaction? Would this one work? Yes or no? Would that give you products, or would it stay as the reactant? Anybody try this one? Would this one work? Would sodium hydride work as a base, deprotonating a terminal alkyne? What do you say, yay or nay? There were a few bases we saw that could deprotonate a terminal alkyne. Is this one of them? That's my question. Well, the answer is yes. Okay, sodium amide, or sodium hydride rather, will work. Okay, if we draw out the Lewis structure, you have sodium, then you have the hydride ion. Well, the hydride ion is going to rip off the proton here, and you're going to end up with the alkyne, which looks like this. Plus, you're going to end up with hydrogen gas, okay? And then, of course, you have the sodium cation here. But the pKa of the terminal hydrogen is 25, and the pKa of hydrogen is around 38. So pKa is equal to 38. The equilibrium is going to lie to the side of the weaker acid, and therefore sodium hydride is very effective at deprotonating a terminal alkyne. So remember, this is called sodium hydride. All right. There we go. Let's move on from there. Let's take a look at this one, and maybe after we're finished this, we'll take a break, and then we'll take a look at some Chapter 10 chemistry. So this is a good problem because it really forces you to practice all of your reagents. Let's see, where do you want to start? Why don't we start at high noon? We'll start here. We're adding HCl across the triple bond. It's being added in a Markovnikov fashion. Right, this reaction here. You see that this carbon in red, the one that takes the chlorine, this one in blue is the one that takes the hydrogen. So you would need just HCl to do that. And you would only need one equivalent of it because this is a Markovnikov addition. All right. And again, stop me if you have a question on any of these. The next one is we're reducing a terminal alkyne to a terminal alkene. We just saw this one as well. We said the only way to do that, you cannot use sodium metal reduction. You've got to use hydrogen gas and Lindlar's catalyst. What about the next one? What about if I want to take that terminal alkyne and I want to get a carboxylic acid from it? Could anybody tell me what the conditions would be for this one that I have in the big red oval? Could anybody tell me even what the first reagent would be? Yeah, absolutely. Thanks, Luke. Yep, 100% correct. So it's going to be ozone followed by water. The next one is the methyl ketone. Of course, you end up getting this from the enol. So you would end up making this enol. Oops, that's not a very good double bond. There we go. No, it's not better either. I find it so hard to draw a straight line with the iPad sometimes. There we go. So you would end up with this enol. So that's a Markovnikov addition of water. So for that, we're going to need mercuric sulfate, sulfuric acid, and water. The next one is an aldehyde, and that comes from a different enol. That comes from this enol, oops, where we have the hydroxyl on the end, like this. So that's an anti-Markovnikov addition of water. We don't just use borane and THF. We use 9-BBN, or you can write R2BH. I'll put 9-BBN, 9-borobicyclononane, right? We looked at the naming of that the other day, just quickly. I won't quiz you on that, but it was fun to look at. The next one, we want to make a Geminal Dihalide. So for that, we're just going to use excess HBr, just bromin or HBr the heck out of it, so to speak. So we'll put HBr, I forgot, excess there. And the last one, we're taking an alkyne and we're just reducing it all the way down to an alkane. That's just straightforward hydrogenation. So we'll put in here H2, whoops, that's not right. There we go. We'll use H2 and we'll just use palladium. And you can pick platinum or nickel, either one. Any questions about those reactions? Is everybody feeling even part of the way confident in these? Even if you're 60% of the way and say, you know what, I kind of get it, Mr. Dion. I'm going to need to study, but I'll get it, you know. Okay, good. All right. A lot of chemistry in there to know. Right. Covered all those.